video, we're going to look at the student's t-model. So remember that the central limit theorem says all we need to model the sampling distribution of y bar is large random samples of quantitative data. And the true population standard deviation sigma, which we don't have. So that's a problem. We don't always know sigma. So we are going to estimate sigma with S. S, remember, the sample statistic does a very good job of estimating what the population parameter standard deviation is. The resulting standard error is just S divided by the square root of n. Okay, so the only difference is instead of using sigma divided by the square root of the sample size, we're going to use S, which is the standard deviation of the sample divided by the square root of the sample size. So a sample standard deviation S, like any other statistic, varies, right? We have natural variation from sample to sample. This extra variation in the standard error was messing up the p-values a long time ago, which also was messing up the margins of error when they were doing confidence intervals. So a statistician named William Gossett, he's actually thought of as the founder of modern statistics. He realized that not only do we need to allow for the extra variation with larger margins of error and p-values, we also need a new sampling distribution model. And it depends on the sample size. So this model became known as the student's t-model. And if you want to read about why he called it that, you can read the textbook, chapter 22. It goes into a little detail about how he had to publish all of this anonymously. So the student's t-model is a sampling distribution model that's always bell-shaped, which we like because that's the normal model. But the details change with different sample sizes. So one thing to note is when the sample size is very large, the model is nearly normal. But when it's small, the tails of the distribution are much fatter than in a normal distribution. Okay, and you can see here, if you scroll to the next page, the dashed is actually the normal model, and the solid curve there is the t-model. Okay, and you can see here, like we said, that when the sample size is very large, the model is nearly normal. That means that values far from the mean. So in the case of like the t-model, for instance, when it's small, the tails of the distribution are much fatter. And you can see on the solid curve how the tails are fatter than the dashed curve, the normal curve. So that means that values far from the mean are more common, especially for small samples. So which makes sense, right? Like, because all of this under here represents the area of the probability. So the further out you are, the more common the values you are for the t-model. So the t-model had to be adjusted, and the student t-models form a whole family of related distributions that depend on a parameter known as degrees of freedom. And the degrees of freedom of a distribution represents the number of independent quantities that are left after we've estimated the model's other parameters, but before we've estimated sigma with S. So because we are basically missing sigma, but we're using S, we have our missing parameter. To find the degrees of freedom, which we notate df, you just subtract 1 from the sample size. So this is the formula, if you want to call it, for degrees of freedom. It's just the sample size minus 1. The one parameter that we estimated was mu. Okay, and remember, we do that because in our sampling distribution, all of our y bars will pile around the true mean, which is mu. So again, the central limit theorem tells us that when we have we take large enough samples over and over and over again of the same size, that our y bar will equal mu. So the sample mean will equal the population mean. Let's look at some ways to perform confidence intervals, and then we'll look at hypothesis tests. So to make confidence intervals or test hypotheses, we need to keep in mind the following. So no longer are we going to be finding z, since we're not using the normal model, so to speak. We're using the t-model. And to find it, it's the same formula. It's the value minus the mean divided by the standard deviation. In this case, my value is going to be y bar, and you're going to subtract mu. And then we're dividing by the standard error of y bar, because remember, we don't know sigma. So we have to use S, which is the sample standard deviation, and divide that by the square root of the sample size. So to find a one sample t interval, a confidence interval, remember the generic formula is just the point estimate plus or minus the critical value times the standard error. And this piece here gives us the margin of error. So here our point estimate is y bar, and our critical value is not z star anymore. It's going to be t star, and our little subscript is n minus 1, which is the degrees of freedom. And then we multiply that by the standard error of y bar. And remember, we find that by doing S divided by the square root of n. So keep in mind the critical value depends on the particular confidence level that you specify and on the number of degrees of freedom, which we will get from the sample size. Okay, so let's take a look at how that's done. You can pause the video and read the problem, and then we'll find the confidence interval together. In 2004, a team of researchers published a study of contaminants in farmed salmon. Fish from many sources were analyzed for 14 organic contaminants. The study expressed concerns about the level of contaminants found. One of those was the insecticide Murex, which has been shown to be carcinogenic and is suspected to be toxic to the liver, kidneys, and endocrine system. One farm in particular produced salmon with very high levels of Murex. After those outliers are removed, summaries for the Murex concentration in parts per million in the rest of the farmed salmon are given. So we can see our sample size is 150. Our sample mean is 0.0913 parts per million, and our standard deviation is 0.0495 parts per million. What does a 95% confidence interval say about Murex? So what I need is my point estimate, which we know is y bar, and then it's plus or minus. So next I need my t critical value, degrees of freedom, okay? So let's talk about that for a second. So let me slide this down. So to find the degrees of freedom, remember it's just n minus 1, so n is 150, subtracted by 1, you get 149. So basically what I'm finding is T 149. Okay, now there's a couple ways you could do this. You could do it on your calculator, or you can go to table T in Canvas. So if we go to the modules and you go under course resources, you'll see the T table there. Okay, I have that in my Notability as well, so I'm going to go to that. Okay, not the Z table, but the T table, which looks like this. And you can see the different confidence intervals, the confidence levels, and then you can see the degrees of freedom. So our degrees of freedom is 149. So if you note, there is no 149 here, okay? So what you do is you would round up. So your critical value here, since I'm looking at 95%, you would go to 1.960. Okay, now, normally what you do, however, is you would go backwards. So let's say my degrees of freedom was 47. There's no 47 here, okay? You would go back to 40. So if I'm looking at 95%, I know that my critical value would be 2.021. If I was, say, finding, my degrees of freedom, let's say, was 99, you would not go to 100, you would go back to 80. So we're more conservative when finding critical values. Always go back. The only time you go up is if you're past the 100. So since I'm past 100, my degrees of freedom is 149. I basically go here and I just use 1.960. That's a good estimate. If you use your calculator to figure out the value, you might get something a little bit different, okay? So we're just going to use 1.960. Okay. So let's go back here to the notes. All right. So I'm going to put here that this is basically T star 100, or it was the Z critical, I think they called it in your table, and that was equal to 1.960. So that's what I'm going to substitute here. Okay, and then I need to find my standard error, and I find that by taking the standard deviation of my sample, and then remember you're dividing by the square root of the sample size. Okay, so let me calculate my margin of error right here. So 1.960, and then I'm going to multiply that by 0.0495 divided by the square root of 150, and I get, for my margin of error, 0.008. Actually, I should do 7.9. We'll go to 4 places since the point estimate is also 4 places. So I'm going to carry my point estimate down here. Okay, and then I'm going to create my interval. So I'm going to do 0.0913 minus 0.0079. And I get, for my lower bound, I get 0.0834. And then if I change that to 0.0913 plus 0.0079, for my upper bound, I get 0.0992. Okay, so what does that mean? Remember, it means that we're 95% confident that the mean level of murex concentration in farm-raised salmon is between 0.0834 and 0.0992 parts per million. And that's the end of this video. Please come back and we'll talk about hypothesis testing for means.